Today we will learn about the case studies on parametric design for climate-responsive architecture. 3 cases from different countries are explained for this training, which are Masdar City from United Arab Emirates, The Edge from Amsterdam, Singapore Housing Board. After case study demonstration, comparative insights about the cases were indicated. The learning objectives of the training are: analyze global case studies to understand how different regions integrate passive urban morphology and active smart systems for climate resilience. Evaluate the role of parametric tools and real-time sensor networks in optimizing building performance, energy efficiency, and occupant well-being. Identify strategies for balancing conflicting goals, such as thermal comfort and daylighting, through multi-objective optimization and data-driven simulation. Masdar City creates a spatial morphology rooted in ecological sustainability that combines traditional Middle Eastern design elements with modern innovations to adapt to Abu Dhabi's arid climate. Compact and low-rise. The city utilizes a high-density, low-rise structure designed to minimize urban sprawl and reduce energy consumption. It is described as a compact, pedestrian-oriented morphology. Street orientation and shading. The city employs traditional passive cooling strategies, most notably narrow, shaded streets and green linear corridors. These spatial configurations are designed to mitigate heat, enhance natural ventilation, channel cool air, and expel hot air. Mixed-use neighborhoods. Masdar departs from rigid zoning by implementing a mixed-use strategy that blends residential, commercial, and recreational spaces to foster vibrancy and social inclusivity, echoing the structure of traditional Arab cities. The current master plan emphasizes distinct neighborhoods linked by sustainable mobility networks. Evolution of form. The original 2008 master plan envisioned the entire city built on a 9-meter raised platform, podium, with a personal rapid transit (PRT) system running underneath. This concept was abandoned due to cost and complexity in favor of a simpler, incrementally built, ground-level development. The design logics and guidelines used to shape the shaded streets and buildings can be listed as passive design principles. The primary tool for shaping the city is the application of passive design principles. This involves orienting buildings to optimize natural daylight while controlling solar heat gain and using wind towers to regulate airflow. Design guidelines. The city developed the Masdar Energy Design Guidelines, MEDG, which drew from rigorous international standards like the German Passive House Code to dictate building performance. Regulatory frameworks. The city's form is regulated by Estidama, a locally developed sustainability rating framework, the Pearl rating system, which standardized construction practices to ensure environmental performance. In summary, Masdar's urban form is defined by a vernacular modern hybrid approach that prioritizes passive cooling and walkability over the hyper-technological futurism seen in other regional projects. Masdar City were designed through a combination of passive urban design strategies, active renewable energy infrastructure, and regulatory frameworks, especially for the integrated solar analysis and wind solutions. The primary strategy for Masdar City involves reducing energy demand through bioclimatic design that adapts to the local arid climate before applying active technological solutions. Wind solutions, passive cooling. The city utilizes wind towers, a modern interpretation of traditional Arab architectural elements, to regulate airflow and enhance natural ventilation. The urban morphology features narrow, shaded streets and green linear corridors designed to channel cool air while expelling hot air, improving outdoor thermal comfort. Solar analysis, orientation and shading. Buildings are oriented to optimize natural daylight while simultaneously controlling solar heat gain to balance illumination with thermal efficiency. The city employs high-performance facades and shaded courtyards to minimize the need for mechanical cooling. Compact morphology. The city utilizes a high-density, low-rise structure to minimize urban sprawl and reduce energy consumption. Masdar City acts as a living laboratory for testing and deploying renewable energy technologies, primarily focusing on solar power. Solar photovoltaic (PV) plants. The city's infrastructure includes a 10 MW solar photovoltaic plant and 1 MW of rooftop PV panels. These facilities feed clean energy to the city and complement Abu Dhabi's broader solar build-out. Research and testing. The city hosts research facilities such as the Masdar Solar Hub, which includes a photovoltaic test center and a CPV, concentrated photovoltaic, testing facility. These facilities allow for the testing of advanced technologies under local environmental conditions. Wind energy. While solar is the primary focus, the city's renewable energy infrastructure also includes allocations for wind turbines alongside solar panels. Regional influence. Masdar spearheaded the development of the Shams 1 concentrated solar power (CSP) plant, a 100 megawatts facility in Abu Dhabi, establishing precedents for large-scale renewable energy in the region. The integration of these solutions is governed by specific design guidelines and rating systems that dictate building performance. Masdar Energy Design Guidelines (MEDG). The city developed its own rigorous standards, drawing from international codes like the German Passive House standard, to ensure high building performance. Estidama Pearl Rating System. Construction is regulated by the Estidama Sustainability Rating Framework. All developed property in Masdar City must achieve at least a 3 Pearl rating, comparable to LEED Gold, which exceeds the minimum requirements for other buildings in Abu Dhabi. Performance targets. Current sustainability objectives include a 40% reduction in energy consumption for its buildings relative to comparable structures in Abu Dhabi. It is important to note that the strategy for implementing these solutions has evolved. The original 2008 master plan, which envisioned the city built on a raised platform, podium, to facilitate transportation and infrastructure, was abandoned in favor of a more gradual, ground-level development to reduce costs. Consequently, the city shifted from a strict, zero-carbon goal to a low-carbon strategy that emphasizes passive design and replicable urban models over expensive, exclusive technologies. Masdar City prioritizes pedestrian comfort through a bioclimatic, compact urban morphology that employs traditional passive cooling strategies, such as narrow, shaded streets and green linear corridors, to mitigate heat and enhance natural ventilation, thereby making walking a viable option for much of the year. This focus on passive design complements the city's energy performance goals, which have evolved from an initial zero-carbon vision to a low-carbon strategy targeting a 40% reduction in energy consumption relative to comparable buildings in Abu Dhabi. To achieve these metrics, the city enforces rigorous sustainability standards, such as the Estidama 3 Pearl rating, resulting in high-performance structures like the Siemens headquarters that consume significantly less electricity than regional benchmarks while integrating renewable energy sources to further reduce the urban carbon footprint. The Edge in Amsterdam, designed by PLP Architecture, creates a dynamic measure in architecture by integrating intelligent technologies that allow the building to adapt in real time to environmental conditions. The project features an interconnected network of environmental sensors that constantly monitor natural light, temperature, and occupancy to optimize the interior environment. Specifically regarding lighting, the system modulates artificial light levels based on the available natural light, which reduces energy consumption and enhances occupant well-being, while simultaneously adjusting heating and cooling systems via advanced algorithms to respond to external climate variations. The daylighting optimization for the Edge in Amsterdam was achieved through the design of a responsive, dynamic system rather than relying solely on static architectural measures. The design integrates sophisticated technological systems to optimize light through the following methods. Real-time monitoring. The building is equipped with an interconnected network of environmental sensors that constantly monitor specific parameters, including natural light, temperature, and space occupancy. Dynamic modulation. Instead of a fixed lighting scheme, the design utilizes advanced algorithms to analyze sensor data and dynamically adjust interior conditions. Specifically, artificial light is modulated based on the available natural light, which allows the building to adapt instantly to changing environmental conditions. Energy and well-being goals. This active optimization strategy was designed to reduce energy consumption while simultaneously improving occupant well-being by balancing natural and artificial light sources. The Edge in Amsterdam by PLP Architecture. The system functions as a digital and sensor-based responsive network rather than a mechanical parametric facade. The system works regarding energy use and environmental control. Real-time data analysis. The building utilizes an interconnected network of environmental sensors that constantly monitor specific parameters, including natural light, temperature, and space occupancy. Energy reduction. Instead of relying solely on physical shielding, the system reduces energy consumption through modulation. Advanced algorithms analyze the sensor data to dynamically adjust artificial lighting levels based on the amount of available natural light. Thermal control. The system also adapts heating and cooling systems in real time to respond to external climate variations, further optimizing energy efficiency. The Edge in Amsterdam, designed by PLP Architecture, achieves high performance and occupant satisfaction by integrating sophisticated intelligent technologies that introduce a dynamic measure into the architectural fabric, allowing the building to adapt in real time to environmental needs. This responsiveness is driven by an interconnected network of environmental sensors that constantly monitor parameters such as temperature, natural light, and space occupancy. Advanced algorithms analyze this data to dynamically adjust interior environmental conditions, resulting in the following performance and satisfaction benefits. Energy efficiency. The system optimizes efficiency by modulating artificial light based on available natural light and adapting heating and cooling systems in real time to respond to external climate variations. Occupant well-being. The modulation of lighting and climate contributes directly to improved occupant well-being. Continuous learning. The design functions as a responsive system that continuously learns from its surroundings, establishing a real-time connection between the architecture and the environment. Scientific analysis regarding energy performance, air quality, and occupant satisfaction confirms that this dynamic, technology-driven approach tangibly improves the sustainability and efficiency of the built space. Singapore's Housing and Development Board, HDB, was established in 1960 to address a national housing crisis and has since succeeded in housing between 80% and 87% of the nation's resident population through a strategy of total design. To optimize scarce land resources, the HDB utilizes a high-rise, high-density morphology consisting of tower and slab blocks ranging from 10 to 40 stories, organized into self-sufficient, new towns that decentralize the population. The board's approach has evolved from initial utilitarian, emergency prototypes to higher-quality standard units, underpinned by a unique economic model that combines decommodification with market principles. This includes universal eligibility for nearly 90% of households and financing via the state-managed Central Provident Fund, CPF. Housing and Development Board Design Strategies, Passive Management. Historically, the Housing and Development Board managed solar radiation and wind through urban planning and typological design rather than computational simulation. Orientation. In the development of early estates like Queenstown, HDB slab blocks were predominantly oriented north-south. This strategy was explicitly adopted to avoid direct solar radiation from the east and west sun, thereby minimizing heat gain. Block typology. The HDB evolved its block designs, slab versus tower, to balance efficiency and environmental exposure. Slab blocks. These 12-story blocks were used to define precinct boundaries and enclosures. Their ventilation effectiveness depends on the length of wall surface in contact with the exterior, calculated per unit. Tower blocks. Developed for larger 5-room units, these layouts were highly inflected to increase vertical surface area. This design was necessary because of the requirement that all rooms, including bathrooms and kitchens, have natural ventilation, which would be difficult to achieve with smaller units in a tower configuration due to the ratio of circulation to net floor area. The parametric logic is applied to Singaporean housing. Static regulatory parameters, URA and HDB. While not dynamic software scenarios, Singapore's planning authorities employ specific geometric rules and modular logic that function as static parameters to shape urban form. Gross floor area, GFA, exemptions. To encourage the greening of high-rise environments, the Urban Redevelopment Authority, URA, introduced development control parameters that influence HDB designs. Specifically, balconies or terraces that are open to the sky are exempted from the maximum permissible GFA. This is calculated using a geometric rule. The area must fall within a 45-degree line projected from the top edge of the opening. This rule encourages a specific building morphology, terracing, to achieve a tropical city aesthetic. Modular construction logic. Historically, the HDB utilized a modular system based on construction dimensions rather than anthropomorphic measures. This system used a grid of 3 meters horizontally and 2 meters vertically to generate room sizes and floor-to-floor heights. This standardized logic allowed for the rapid proliferation of specific block types, slab and tower blocks, across the city-state. The three cases illustrate a spectrum of responsiveness, ranging from real-time sensor actuation to algorithmic design optimization and static urban morphology. Masdar City, UAE, Morphological and Technocratic Systems. Masdar utilizes a hybrid approach of passive urban morphology and active smart systems. Responsiveness is achieved through a compact, high-density, low-rise, urban form inspired by traditional Arab cities, designed to channel cool air and shade walkways, passive cooling. This is layered with smart city features, such as digital infrastructure and data-driven energy optimization. However, critics note that Masdar's responsiveness is often defined by top-down, technocratic control rather than the granular, user-centric adaptability seen in the Edge or the social optimization of Singapore's public housing models. The Edge, Amsterdam, real-time active adaptation. The Edge represents a dynamic, responsive system where parametric logic is embedded into the building's daily operation rather than just its initial form. The building utilizes an interconnected network of environmental sensors to monitor occupancy, temperature, and light. Advanced algorithms analyze this data to modulate artificial lighting and climate control in real time, effectively introducing a dynamic measure that adapts instantly to environmental variations. This fine-grained responsiveness focuses on the immediate comfort of the individual user and operational energy efficiency. Singapore housing. Algorithmic multi-objective optimization. In the context of Singapore's tropical climate, responsiveness is achieved through computational simulation during the design phase. Researchers utilize multi-objective optimization tools, coupling JE++ EA with Energy+, to balance conflicting environmental variables. The design process treats specific elements, such as window-to-wall ratio, WWR, overhang projection, and orientation, as variables to optimize for the triple bottom line: social, environmental, financial. Unlike the Edge's active sensors, Singapore's responsiveness is embedded in the static geometry of the building envelope, optimized to maximize natural cooling and daylighting while minimizing solar heat gain before construction begins. The projects demonstrate different methods of integrating form and function, relying on varying types of feedback loops, computational versus operational. Masdar, strategic loops. Masdar's feedback loops are macro-scale and longitudinal. The project was envisioned as a living laboratory, meaning the city itself is a prototype. Feedback from early phases, e.g., the high cost and complexity of the personal rapid transit system, led to significant revisions of the master plan and a shift from a zero-carbon to a low-carbon goal. However, the project has been criticized because its spatial morphology, the physical form, was prioritized as a branding tool, occasionally creating a disconnect between the symbolic form and the actual social function or livability for non-elite residents. The Edge, operational loops, form and function are integrated through the Internet of Things. The building functioning as a responsive system that continuously learns implies a feedback loop where data on user behavior and external weather directly alters the building's internal state, e.g., dimming lights, adjusting heating. This integration allows the architecture to function as a score of creativity that adapts to changing needs. Singapore simulation loops. The integration of form and function is driven by sensitivity analysis. For instance, the study found that overhang projection has a positive correlation with thermal comfort but a negative correlation with visual comfort, daylighting. The feedback loop here is computational. The design team iterates through thousands of permutations to find the Pareto optimal solutions that balance these conflicting functional requirements without sacrificing the building's energy efficiency. The divergence in success between these projects highlights the critical importance of aligning modeling goals with stakeholder realities. Masdar, misalignment and calibration. Masdar faced challenges due to a misalignment between its utopian vision and market realities. The project was driven by a centralized, technocratic governance model with limited stakeholder inclusivity. While early modeling promised a zero-waste, zero-carbon city, the lack of broader stakeholder buy-in, beyond state elites, and the high cost of technologies led to a reality gap. The project's survival and partial success have depended on recalibrating the vision to be more commercially viable and incrementally developed, shifting from a rigid master plan to one that allows for phased growth. The EDGE, user-centric alignment. Success was achieved by aligning the technological capacity of the building with the specific needs of the primary tenant, Deloitte, and the developer, PLP architecture. The dynamic measure was successful because it tangibly improved occupant well-being and energy efficiency, creating a clear value proposition for the stakeholders involved. Singapore, holistic alignment. The Singapore approach emphasizes the triple bottom line, explicitly mapping social needs, thermal, visual comfort, alongside financial, life cycle cost, and environmental goals. Success is tied to early-stage modeling that identifies the most influential variables, e.g., light efficiency and air conditioner COP, to prevent costly late-stage changes. This method ensures that the resulting housing is not just energy efficient but also cost-effective and habitable for the specific population density of Singapore. The transition from intuition to simulation-based design intelligence is exemplified by the strategies of the EDGE in Amsterdam, Singaporean housing, and Masdar City, which collectively demonstrate how parametric methods optimize climate performance across building and urban scales. In Amsterdam, the EDGE redefines the building envelope as a dynamic system where algorithms analyze real-time sensor data to actively modulate lighting and climate conditions, thereby transforming static architecture into a responsive interface. In Singapore, the complexity of achieving net zero energy in high-density housing necessitates moving beyond intuition to multi-objective optimization. Researchers couple simulation engines like Energy Plus with evolutionary algorithms to mathematically resolve trade-offs between daylighting and thermal comfort variables before construction. Expanding this logic to the urban scale, Masdar City operates as a living laboratory that integrates technocratic planning with passive design morphology, utilizing advanced data to align infrastructure with renewable energy goals and environmental responsiveness.